Greetings to our instructor, Dr. Razali. My name is Nur Hakim Arif bin Muhammad Razali. So I would like to present about our project. So this is our introduction to industrial temperature control. So first, it is important to understand that regulation is one of the most vital challenge in process control. It affects a wide range of critical engineering systems, including chemical reactor, industrial furnace, and food processing machinery. So secondly, when we look at the system dynamic, so when we look at the industrial plants, they often exhibit a slow response. This is primarily due to thermal inertia, which means the output temperature does not change instantly the moment the heating input is adjusted. So third is our project response characteristic. So this delay typically result in what we call an S-shaped reaction curve. So in this scenario, the temperature gradually increase and require a significant amount of time to reach a stable steady state. Next is control implementation. So to manage the control implementation, this challenge we use feedback control. So this process continuously compared to the actual measured temperature against our target set point. We then implement a PID controller to minimize the error between the two through proportional, integral, and derivative action. So finally, for our project analysis, the system is represented using a second order transfer function. So the specific model we are using is Ts equal to 10 over 20 square root plus 12s plus 1. So next, let's talk about what we actually trying to achieve here, our project objective. So we have 5 main goals for this study. First, getting the model right. We want to build a realistic digital version of a temperature plant in MATLAB so we can test it behavior safely. So secondly is redesigning a smart controller. We aren't just using one method. We're tuning PI, and PID controller using the old school Ziegler-Nichols technique and comparing it with the modern auto tuner. Thirdly, we're checking how it reacts. So we want to see the difference between open loop and closed loop system by looking at key metrics like how fast it responds and whether it overshoot the target. Then we picking the best approach. In a factory, you want a system that is stable and safe, so we look into the controller that balance speed and reliability. Finally, we're connecting to the global goals, SDG. We want to show how smart engineering helps reach the UN Sustainable Development Goals, specifically in making industry more energy efficient and sustainable. That's the roadmap of our project. Now let's move on to the methodology.
Now I will explain method 1. This method is used to find the best value for the BID controller parameters KB, KI, and KD. First, we do open loop analyze. This means we remove the feedback and apply a step input of the system. Then we observe it, the output and draw the process reaction curve, which show how the system responds over time. Second, we do a parameter extraction from the step response curve. We find two important values, L, which is the time delay or lag time, and T, which is the time constant of the system. To find this value accurately, we draw a tangent line at the step set point of the curve and measure L and T from the graph. Third, we do the calculation step. We use the value of L and T in the Ziegler-Nichols formula table to calculate the controller against KB, KI, and KD. Finally, these parameters are used in the BID controller to improve the system performance, making it fast and more stable. And next, methodology 2, automate BID tagging. In the method, the controller parameters are tagged automatically using software. First, we create a closed loop system in Simulink. with the negative feedback. Then we insert the PID controller block before the blend transfer function. Second, we open the PID tuner app inside the controller block. We select the transfer function based tonguing option, and the software automatically calculate stable value for the controller gains. Third, we perform optimization. The tuner adjusts the B, I, and D parameters to balance response speed and system stability. We also compare different controller types such as B, only BI, and BID to see how each one affects the system response. This method is fast, easy, and reduce human error compared to manual tonguing, and that is all.
I'm Alexander Karasang, CE24071. I'm going to present about the open loop analysis using our MATLAB. This is our coding. So to begin our project, first we need to understand how our industrial temperature plant behave naturally without any external control. So we wrote this MATLAB script to simulate how open loop response, which is our foundation for our entire tuning process. So in the code, you can see we define our second order transfer function G as with a numerator of 10 and also denominator coefficient of 20, 12, and 1. This represents the physical dynamics of heating system by using the step G command. So we apply a unit step input to observe the system reaction. So let's see the graph. Okay, once run, as you can see, the graph shows a S-curve. As you can see from this plot, the temperature doesn't jump immediately. It follows a slow S-shaped path here, curve go up. So this confirms that the presence of thermal inertia, where the heat transfer process causes a delayed response. So as you can see here, our steady state K reaches 10. So our delay time is roughly below here, where we think it's approximately is 1.1, around here below where it starts, measure 1.1. And for our time constant, it's around here, 15 seconds. So while this open loop is system stable, so it's far too low and cannot correct itself. And then, however, operating these values were essential because the exact inputs we need to calculate for our controller gains is using the Ziegler-Nichols method. Open our plant parameters from S-curve. Then next we're going to translate those physical characteristics to controller gains. This script performs the mathematical call for our Ziegler-Nichols tuning method. As you can see in this code, this is our K, L, and T, which K is our system gain, L is our delay time, and T is our time constant. So this script then applies then the ZM formulas for our PID controller. To find our proportionate gain, Kp, we use our ratio of T and 2 to L. So it's this the scale by 1.2 adjusted for our plant gain of 10. And then this gives us Kp of exactly 1.64 when we run it. So here let's go see. Our Kp is 1.64, Ki is 0.744, and Kd is 0.900. This is just our coding calculation, but when we are doing our manual calculation, this should be 1.64, this Ki will be 0.745, and our Kd is 0.902. So then we used all this, we make it a variable and Simulink parallel PID block. Then it will convert into our Ki 0.745 and our Kd 0.902. So to finalize our analysis, we move from the Simulink environment to our pure MATLAB script to validate our results. So this ensures our findings are not just simulation specific but our mathematical sound. So this is our ZN, which is our Ziegler-Nichols versus our auto PID. And then in this section of the code, we define our industrial G as here 10, 20, 12, and 1. So here's our Ziegler's 1.64, 0.745, and 0.902. And this is our auto tune, Kp auto tune, Ki auto tune, and Kd auto tune, 0.9792, 0.0256, and 0.182. So the most critical part of this, we use feedback command. So feedback command, this creates a unity negative feedback loop. simulating exactly how the physical system would behave with the sensor continuously feeding the temperature back to the controller. So let's run the command. Okay, as you can see here, Ziegler-Nichols is our red line, and our blue line will be our auto-tune PID. So here you can see the difference between two of them, which then you see the red line here is spiked quickly, but then oscillates heavily and remains steady state till the end. And then for our auto-tune, the blue line is much more disciplined, so it reaching the set point smoothly until it overshoots minimally. So in this step function, it's very vital for our report to make because it calculates as you see, it calculates our rise time, setting time, or peak overshoot for our final comparison tables. So these data confirms that the industrial safety energy efficiency. The auto-tune PID is the superior choice as it ensures the system reaches steady state without any dangerous temperature spikes. So first, here's our 4 different type of loop. This is our open loop, closed loop without PID tuning, closed loop with using Ziegler-Nichols tuning, and lastly our closed loop using auto-tune tuning. Okay, let's see our open loop scope with. Let's run. Okay, let's see. This is our scope. As you can see, this is here. It starts from 0 and then it go to 10 and it will be in steady state at 10 all along the way. So this natural behavior of this plant is slow with a steady state of 10 for a unit, and it keeps step input because it lacks ability to correct for any disturbance here. So as you can see, we have a natural S-curve system and has 0 overshoot. So far, it's slow for industrial use because it takes over 30 seconds and for feedback to tell if this system haven't reached a set point yet. So next, we're going to see our without PID tuning. Okay, for PID tuning, you can see a bit different as for our open loop, and it stays between 1 and 1.2, roughly 1.1. And then our Ziegler-Nichols tuning, our output will be the wave will go up to 1.4, it will overshoot, and then we will go steady state at 1. And for PID auto tune, you can see it go up roughly above 1, and then it will go steady state. So you can see the difference between these 3 waveforms. Because you see, if without PID tuning, it's simply adding unity negative feedback, which you can see here. So the rise time improve. However, the plant is second order system, so the baseline is created to overshoot and oscillates. So it shows us that the feedback alone is not enough to achieve the higher performance. As for the Ziegler-Nichols PID, as you can see here, so this method is all about speed. So it gives us a faster rise until 1.4 here, and then it will just can see here is extremely aggressive because it produces a pretty massive overshoot here, and then it will go back down and going to steady state. So if in industrial furnace or chemical reactor, I think everything is quite suitable to leading to equip for damage and ruin. It could be catastrophic, so it could spoil our equipment and damage our products batches. So this is not so suitable. And then for our lastly, with PID tuning. So this auto-tune PID tuning result for wave. So this is very recommend. Well, it raises, then it slowly decreases and going back smoothly for a stable response. So it only overshoots for nearly I think 7.3% overshoot here, and then it has 0 steady state error. So this balance occurs. It ensures that the temperature reaches the set point safely, so that it will not waste any energy through our oscillations.
So Assalamu alaikum warahmatullah. This is the presentation for our temperature transfer function for the closed loop system and the open loop system. So we combine in this Simulink file the open loop and the closed loop with the calculated tone and the auto tone all in one file. So as we see here, this is the closed loop function or the closed loop system without any PID, without any tuning. So let's run first. So let's open the open loop system first. So double click on the scope. Then this is the result. So the value here reached 10 because the K value here is 10. That's why the value reached 10 and it started increasing gradually as we see here. But the system doesn't have any feedback or any kind of feedback. So let's run the closed loop one. So this is the plot that we got. Actually, the value here is only 1 because the unit function that we use, we always set 1 volt. But the problem here with the feedback system or with the closed loop system, that the value didn't reach 1. It doesn't reach 1. It will not reach 1 because it doesn't have any tuning. So that's why it doesn't reach 1. So actually the tuning should fix this overshoot and fix the amplitude value. So let's see the calculated tuning. So we use for the P 1.64 and for the I 0.745 and for the D it's 0.92. So this is the plot. So actually it's overshoot. That's why the auto tuning or the PID for the open loop system is kind of meaningless. So let's see how it affects the closed loop one. So it also overshoot, but the PID fixed the amplitude problem. So it now fixed at 1 as the unit step function. So the built-in MATLAB function for the auto tune, it fixed that problem for the closed loop system. But for the open loop one, it still remain the same. It overshoot. It's also, we can say about it, it's just kind of meaningless. So let's see how it affects the closed loop one. So actually the values here for the PID, the P is 1.82, the I is 0.0256, and for the D it's 0.192. So let's double click on the scope. So now we get smooth curve, although it overshoot but not that much. As we see here it's 1.2, so it shoot by 1.1 or less than that because the value here is 1.2, but it's, we can say it's kind of great. So here we combine for the closed loop function or for the closed loop system, we combine the P and the PI and the PID all together in one, and then we display them all in one scope. Let's double click it, see what we'll get. So, this is it. The yellow one is for the auto tune P, and the blue one is the PI tuning, and lastly the orange one is for the PID auto tuning. So as we see here, just fixing the P, it doesn't reach 1, but for the P and I and the PID, it actually got 1. But the difference between the PID and the PI is how it overshoot. So as we see here, the blue one is the PI one, it overshoot more than the PID one. So This is all about the Simulink and the simulation for the temperature system, closed loop and open loop with manual tooling and
Okay, so now I'm going to conclude our presentation. So first thing first, in terms of the achievement of objectives, we will successfully develop and simulated a mathematical model for a temperature control system using MATLAB and Simulink. We implemented both open loop and closed loop configurations and compared their performance. Stable controller designs were achieved using the Ziegler-Nichols tuning method as well as the automated PID tuner. Next, for the key findings, feedback was proven to be very important. The open loop system was unable to compensate for errors, while the closed loop system maintained better stability and accuracy. When comparing controllers, the P controller provided a fast response but suffered from steady state error. The PI controller eliminated steady state error but caused significant overshoot. Overall, the controller delivered the best performance with fast settling time, minimal overshoot, and zero steady state error. Finally, for recommendations, although the Ziegler-Nichols method gives good initial parameters, further manual tuning of the integral and derivative gains is recommended to reduce overshoot. Additionally, the PID tuner requires a well-defined and stable closed-loop model to function effectively. Okay, now I'm going to explain about the SDG, which is SDG stand for Sustainable Development Goals. Okay, there were five SDG, which is first thing first is SDG 7, which is the affordable and clean energy as optimized control system reduce unnecessary energy consumption. Second is SDG 8, which is decent work and economic growth by enhancing industrial productivity, operational safety, and system reliability. Number three is SDG 9, industry and innovation, where efficient temperature control improves the reliability and sustainability of industrial process. Number four is SDG number 12, responsible consumption and production by minimizing waste and improving resource efficiency through precise control. Okay, last SDG is SDG number 13, climate action. Since lowering energy demand helps reduce greenhouse gas emissions. So overall, in our group assignment, it demonstrates how effective control system design can support both industrial performance and sustainability goals. So that's all from us. Thank you.